So far in these lessons on lift, we have considered only two-dimensional airflow, and a sound understanding of this is the foundation for a full appreciation of the actual pattern of airflow around an aircraft. Even small changes of pressure will modify the airstream direction by inducing flow towards any region of lower pressure. This three-dimensional airflow can modify the angle of attack, creating an effective angle of attack. It may increase drag and alter stalling characteristics, and can even influence the control and stability of the aircraft. From now on, instead of just the aerofoil section, we will be considering the entire wing. And as a precursor to the next few lessons, you will need to be familiar with the terminology associated with wings. The wing area is the planned surface area of the wing and has the symbol S for surface. It is deemed to include any part of the wing covered by engine nacelles and the part of the fuselage in line with the wing, since the pressure pattern carries over these areas, allowing them to be legitimately considered as part of the entire area. The wing span, lowercase b, is the distance from wingtip to wingtip, usually now quoted in meters. The chord is the distance from leading edge to trailing edge, and the average chord, lowercase c, is the geometric average. The product of the span and average chord is the wing area. The aspect ratio, or AR, is the proportion of the span and the average chord. That is, B over C. If the plan form is curved, for example like the Spitfire's elliptical wing, an alternative way of determining the aspect ratio is span squared over area. This assumes, of course, that you have a figure for the wing area. The aspect ratio of the wing determines the aerodynamic characteristics and structural weight. For example, a wing area of 100 square meters could be arranged in a high aspect ratio, here 51, or a low aspect ratio of, say, 3. Typical ARs vary from this value for a modern combat aircraft, through 12 for a high-speed jet transport, to 35 for a high-performance sailplane. Continuing with the terminology, we have root chord, which is the chord length at the wing centerline, denoted by CR. Logically, at the other end of the wing is CT, the tip chord. The ratio between these two is known as the taper ratio, CT to CR. The taper ratio affects the lift distribution and the structural weight of the wing. Ratios range from 1 for a rectangular wing to 0 for a delta wing with a pointed tip. For a swept wing, the sweep angle is usually measured as the angle between the line along the wing joining points of 25% chord and a line perpendicular to the root chord or aircraft centerline. Finally, the mean aerodynamic chord, abbreviated to MAC or MAC, is the chord drawn through the geographic center of the plan area. It is located at the reference axis of the aircraft and is a primary reference for longitudinal stability considerations. A rectangular wing of this chord and the same span would have broadly similar pitching moment characteristics.